Good morning all. I Salim, Assistant Professor in Electronics and Instrumentation Engineering Department, Kite Group of Institutions, presenting you modulation used in telemetry. Basically, modulation is used in electronics and telecommunications. Modulation is the process of varying one or more properties of a periodic waveform called carrier signal with a modulating signal that typically contains information to be transmitted. Most radio systems in 20th century used frequency modulation or amplitude modulation for radio broadcast. In modulation, we use modulator and demodulator. A modulator is a device that performs modulation, and a demodulator is a device which demodulate or the inverse of modulation. Here is another term, modem, which is a combination of modulator and demodulator. So here is our first slide, modulation. The purpose of a communication system is to transfer information from a source to destination. In this case, we have a mic and a transmitter. Through this transmitter, I am sending a sound signal from one place to another place, and here is the channel. In between this channel, some noise is also added in my signal. Then at the receiving end, we have receiver and a output device, loudspeaker. So when I generate some sound at some location, it also generated at another location with some noise. In modulation, a message signal which contains the information is used to control the parameter of a carrier signal so as to impress the information on the carrier. The message or modulating signal may be either analog or digital. Analog signals are denoted by MT and digital signals are denoted by DT, and the carrier should be a sine wave or a pulse string. In case of modulation, we generally put our message signal over the carrier signal and then transmit it to one place to another place. Modulation, the basic sine wave Vt is equal to V0 sine 2 pi Ft plus phi. Here Vt is the voltage of signal as a function of time. V0 is the amplitude of the signal, represents the maximum value achieved at each cycle. Small f is the frequency of oscillations, the number of cycles per second, and phi denotes the phase of the signal, representing the starting point of the cycle. To modulate the signal just means to systematically vary one of the three parameters of a signal. The three parameters are amplitude, frequency, or phase. Here are some examples. If the message signal is empty, controls amplitude, it gives me amplitude modulation, also denoted by AM. If the message signal controls frequency, empty controls frequency, then it is called frequency modulation. It is denoted by FN. If the message signal empty controls phase of the signal, it gives me phase modulation. It is denoted by phi n. Amplitude modulation is the simplest of the three to understand. The transmitter just uses the information signal VMT to vary the amplitude of the carrier VCT to produce a modulated signal, a VAMT. Here are three signals in mathematical form: information signal, carrier signal, and its modulated signal. VAMT is our modulated signal through amplitude modulation. Here we see that the amplitude terms has been replaced by the combination of original amplitude plus information signal. This is original amplitude plus information signal. The amount of modulation depends on the amplitude of the information signal. This is usually expressed as ratio of the maximum information signal to the amplitude of the carrier. Modulation index is denoted by M. It is equal to maximum of VMT. It is modulation index is denoted by small m is equal to maximum of VMT divided by VCO. If the information signal is also a simple sine wave, the modulation index will be M is equal to Vm divided by VCO. The interpretation of the modulation index M may be expressed as the fraction of the carrier amplitude that it varies by. If modulation index is 0.5, then the carrier amplitude varies by 50% above and below its original value. If modulation index is 1, then it varies by 100% about its original value. Is the amplitude shift keying. Through this process we can encode our signal. Let we have a signal like this 0 1 0 0 and our carrier signal is like this. This is my carrier signal, and at the after amplitude shift keying modulation we get this type of signal in the output. Here amplitude 1 for logic 0 and amplitude 2 for logic 1. Here A2 is greater than A1 and we get this output after amplitude shift keying. Here is the frequency shift keying. In this, we have a signal like this 0 1 0 0 and this is our carrier signal, and after frequency shift keying modulation we get this type of signal at the output. Here is the 0 frequency, here is the 1 is denoted by this type of frequency, again 0 0. This is my frequency shift keying. Next is our phase shift keying. In this, phase varies as the system changes. Like this, our signal is 0 1 0 0 and it phase shift keying encodes digital data by shifting the phase of carrier signal. Here is our carrier signal, and after phase shift keying modulation we get this type of signal. Here is 0 phase because there is no signal, and at 1 we have a 180 degree phase shift at this place. Then again no change in phase because there is no signal, 0, and again no signal, so 0 phase difference. Here are some differences between ASK, FSK and PSK. Variable characteristic criteria is variable characteristic. In ASK amplitude varies, in FSK frequency varies, in PSK phase varies. Here are the bandwidth of different modulation techniques. Then noise immunity, here is low in amplitude shift keying, high in frequency shift keying, and phase shift gain. Complexity simple, moderate, very complex. Error probability high, low, low. Then performance in presence of noise poor, better than ASK, better than FSK. Means performance in presence of noise PSK is better out of these three. Bit rate 100 bits per second, 1200 bits per second, and more than 1200 bits per second. This is all about modulation. Thank you.